welcome back to yet another video on our channel Equalate Mathematics. We have started lecture series on CSIR NET SET Gate and other competitive exam too. That JEE Mains CT also I included here. Okay, I uploaded plenty of the videos on these topics, on these subjects and exams on my channel. Okay, so we are in my today's lecture we're gonna learn one of the topic from ring theory, which is a subfield. Okay, already I explained field, ring, everything in my previous lecture. If you wanted to see, you may check it into my playlist. In my today's lecture I'm gonna explain to you all the definition of a subfield and along with some of the example and one important theorem, that is a Chinese remainder theorem for ideal, that how we can define ideal by using this theorem. Okay, now let's get started our today's lecture. I'm going to explain to you all each and every concept in detail. Here in my today's lecture, we are going to learn first of all the definition of a subfield. So definition of a subfield is quite similar like a subring, subgroup. Okay, so we have to apply similar properties. Okay, like a subring. In a subring, what we have done, we taken two elements from our element from our ring yes. Okay, and we shown their subtraction it is also in yes and their multiplication it is in also yes. Okay, so it is the definition of a subring. Okay, so similarly we have to apply here for a subfield. Okay, but one more condition here, that subfield need to be a field first, then we can apply these conditions. Okay, now here the definition, let's read. We have yes non-empty subset of F is said to be a subfield of F. Okay, when we say it is a subfield, okay, if yes under addition dot itself a field. Okay, so if you don't know the meaning of a field, the definition of a field and example, you may check into my previous lectures. It is everything is there. Okay, yes under addition dot itself a field. Okay, so or one more definition we use here for finding all A belongs to yes, B belongs to yes, that A minus B also in yes, and second A belongs to yes, B belongs to yes, that dot product A dot B belongs to yes. Okay, it is the definition of subfield. It is quite similar like a subring. Okay, so as we learn in a subring lecture, it is similar like this. Okay, now here let's me explain one of the example for a subfield. Okay, we can see here Q is a non-empty. Okay, Q is a non-empty and which is a subset of R. Okay, and we know that Q under addition dot is a subfield. Okay, of R under addition dot, and it Q under addition dot itself a field first. Okay, it is a already field. I already explained some examples which is similar like this, and Q under addition dot also I explained in my previous lecture, that says that Q under addition dot itself a field. Okay, and Q is non-empty subset of R, then we can see that it is a subfield of R under addition dot. Okay, now second example we may consider here Q of root 2 root 3. Okay, which is a subset of R. Okay, Q of root 2 root 3 goes to R. Okay, and which is non-empty subset of R, and we know that Q of root 2 root 3 under addition dot itself a field first. Okay, it is a field, and if it is a field, then our definition hold here, then we say that it is a field of R under addition dot. Okay, now we are going to move for the next important theorem, which is Chinese remainder theorem. Okay, why it is much important? Because we used to find out the ideals. Okay, whether it is maximal ideal, minimal ideal. Okay, for finding this we use a Chinese remainder theorem. It is very much important. Okay, so you need to understand this theorem first, because after that some of this I'm going to explain some of the question from CSIR NET exam. Okay, which previously asked, so we have to go for this one. But first of all we learn the definition for Chinese remainder theorem, and then we'll go for some examples. Okay, so here if R is commutative ring is unity, I can be written as I1, I2, IN. Okay, so that I is ideal here. Okay, that ideal can expand as a small I1 as a sub ideal, I2 is also ideal, IN is also ideal. Okay, all are the ideals which is generated by that capital I, which is also ideal. Okay, then we write R by ideal generated I can be written as R by ideal generated by I1, I2, IN, which is similar like R by I1, R by I2 up to R by IN. Okay, these all are the ideal generated. Okay, so I return R by I ring by ideal generated by I as a ideal generated by I1 to IN. Okay, these are the ideal which is generated by capital I. Okay, which is isomorphic to R by ideal generated by I1 cross R by ideal generated by I2 up to R by ideal generated by IN. But we have one condition. We need to be very careful about this. Whenever we are trying to find these ideals, that we need to know first of all the GCD of I1 and I2 need to be 1, and I and J, like 1 and 2, these need to be a different, like I and J need to be a other one. So you cannot take the GCD of I1 with the I1. Okay, we want the I1 and IJ, I and IJ, their GCD is 1, but I and J not equal. Okay, now let's see some of the example. Okay, depend on this definition of a Chinese remainder theorem. So I added here one more example. Z generated by Z upon ideal generated by 6. Okay, so ideal generated by 6 can be written as ideal generated by 2 into 3. Okay, and Z upon 2 into 3. So Z upon 2 into 3 can be written as ideal generated by 2 and ideal generated by 3. Okay, so this is the way I written isomorphic to Z by ideal generated by 6. Okay, Z by ideal generated by 2. Okay, Z by ideal generated by n. Okay, so how can we write Z divided by ideal generated by n? We can write it as the isomorphic to Zn. Always remember, Z by ideal generated by n, it can be isomorphic to Zn. It is hold for integer. Okay, so Z by ideal generated by 6 can be written as this way. This one can be written as Z by ideal generated by 6 can be written as Z6, and Z by ideal generated by 2 can be written as Z2, and Z by ideal generated by 3 can be written as Z3. You may verify this one by using group theory, subgroups, groups of Z6. Okay, the properties from Z6. Okay, so you may verify this whether it is equal or not. Okay, you have to find out the number of element here. Okay, order of group here. By using this, you have to verify. Okay, both are coming equal. So this is the property of a Chinese remainder theorem for ideal, it says. Okay, so similarly you may take one more example here, like a Z15. Okay, Z by ideal generated by 15 can be written as Z15. So it can be expanded as 3 into 5. So isomorphic to Z by root 3, ideal generated by 3, and Z by ideal generated by 5. Okay, so Z15 isomorphic to Z3 cross Z5. Okay, so this one is easier, that we can easily say that Z15 isomorphic to Z3 cross Z5. And when we say that two groups are isomorphic, first condition, the element from first group and the element from second group need to be equal, like their order need to be equal. Order from Z15, every element of order from Z15 need to be equal. They need to be a cyclic, they need to be abelian. If this property holds, then we say that these two groups are isomorphic. Okay, now let us see one more last example, which is based on a Chinese remainder theorem for ideal. Here we can see we want the maximal and prime ideal for qx upon x square plus ideal generated by x square minus 1. Okay, so what do? We first of all find the square expanded form of x square minus 1. This is a polynomial, so we can write x square minus 1 square, like x minus 1 x plus 1. Okay, so as I written over here, so x square minus 1 is x minus 1 x plus 1. So GCD of these two elements need to be a 1. Okay, x minus 1 x plus 1 GCD is 1. So how to find the GCD LCM for two polynomials? I already explained it into my previous lecture. Okay, GCD of fx into jx, how can we find? Okay, you may check it into my previous playlist. So we can write ideal generated by qx upon x square minus 1 as x plus 1 x minus 1 and expand it by using a Chinese remainder theorem for ideals. Okay, so we have to use the Chinese remainder theorem for ideal, and it is already commutative, and we can say that it is GCD is also 1 here. Okay, if GCD 1, then we can write it as the ideal qx upon ideal generated by x square minus 1 is isomorphic to qx upon x minus 1 qx upon x plus 1. Okay, and this is the value for q. Okay, so it is the group q, it is also q here. Okay, so q cross q has the two maximal and a prime ideal. So how to find the maximal and a prime ideal? That we explain it into my previous lecture. Okay, or you may go through like every maximal prime ideal of a Zn is a prime divisor of n. It is for Zn. Okay, so we want for qx. If it is a field, then it has a maximal or prime ideal. Okay, then we say that it has a exactly two maximal and prime ideal. Okay, if it is a q is a field, and we know that q is a field itself. Okay, and q cross q, it is having two maximal ideal and prime ideal. Okay, so if you don't know the how to find maximal ideal and prime ideal, you may check it into my previous playlist. You will get the solution for this one. Okay, now q cross q has a two maximal and prime ideal. Okay, if q cross q has a two maximal and prime ideal, it is isomorphic to q of x upon x square minus 1. Okay, that means this one is also having two maximal and prime ideal. Okay, so we got the maximal and prime ideal upon qx of x upon x square minus 1 is a two maximal and prime ideal. Okay, so that's it for our today's lecture. I wanted to explain to you all here the maximal and prime ideal along with the definition of a subfield and Chinese remainder theorem. Okay, in my next lecture we are going to learn some of the question which is depend on maximal and prime ideal. Okay, so thank you for my today's lecture everyone.